Ferrite cores are an amateur radio operator's best friend. These can be used to suppress RFI, they can be used to suppress common mode currents on antenna feed lines, but how well do they actually work at the frequency that you want them to work at? Well, today I'm going to show you how to do that with a simple NanoVNA, and we're going to see a couple of these cores. I'm not quite sure exactly how well they're going to work for my particular application, but we're going to measure them and see if they will do the job properly. So what I want to do is I want to measure to see how well these suppress RFI on the 2 meter band. So I've got a couple of cores here. This is a Mix 31, this is a Mix 43. These are both rings. I've also got a clamp toroid here as well. This is going to be handy because I think a majority of my RFI noise is coming from Ethernet. So without actually unplugging it, which I can't do because it is in a production environment that is on a with customers on it, I can pass an Ethernet cable through here without actually disconnecting it and clamping it straight over the cable. So I want to see how effective this is, particularly at 2 meters. But we'll also have a look at some of these other cores and see how they go predominantly on amateur bands, such as we can have a look on HF as well and see what the effects are and how we can best utilize these too. So we're going to use the NanoVNA. I've got the SAA-2N VNA, and this covers 50 kilohertz to 3 gigahertz. You can use any NanoVNA. The process is going to be very, very similar. And what I've done here is I've built 2 test clips. So this is basically a BNC here on one end and an alligator clip here on the other. I have cut off the braid of the shield of the coax, and I've just soldered the center conductor here to the alligator clip. And what this is going to do is be able to use this on a piece of wire. So I've got here a bit of wire here which we're going to connect to the VNA via these alligator clips, and then we can put our core over this wire and see just how much RFI suppression we get. Now, this method that I'm going to do won't show you how to measure a choke using a piece of coax. You can still use it though using this method. What you will need to do is you'll need to though connect the alligator clips that I've got here in this instance to the outside shield of the coax, because common mode current flows on the outside of the coax shield, so just the shield basically. So what you would do is you would clip this to the outside shield, the other one to the outside shield when you're connecting basically your device under test to your VNA. But because I'm only interested in RFI suppression, I'm not interested in common mode current, I'm not going to be testing with coax today. So the first thing we want to do is go into the stimulus, and we want to set basically our frequency range. So I've got a frequency range here of 3 megahertz through to 200 megahertz. So that's going to cover the HF, 6 meter and 2 meter bands as well. Probably don't need to sweep this entire sweep because I'm only interested in 2 meters, but I just want to show you some of the plots that you actually get and how good these cores are even at some of the HF bands. So we're going to leave it on 3 megahertz to 200. If you do want to change it, you go into here and click start. So we'll go 3 megs, stop 200 megs. And then what we want to do is go back into our calibration. So calibrate. Now I've already calibrated this up, so I'm just going to reset it there so that we start again. Go into calibrate, and we want to put in our open standard into port 1, which is our S11, and let's go open. That's been done. It will take a little bit of time to calibrate because we do have quite a wide frequency range as well. Short. Pop in the load now and click load. We can just tap isolation as well. Just leave the load calibration in, click isolation. And now we want to do through. So let's just remove all of our calibrations now. And because I'm using the NanoVNA with N connectors on here, I need to put in a couple of N to BNCs between both ports. And then I can connect my alligator clips. So I'm going to put the first one on there and onto our other port. And now what we need to do is we need to connect our test wire. So I'm going to connect my test wire to each end here, and I'm just going to clear everything out of the way just so that it's nice and open. Keep it away from sort of any sort of magnets or anything magnetic or anything that's going to affect it. And we'll just go down now and do a through line calibration. And what that's going to do is that's going to remove the effects of this wire and give us a trace at 0 dB across the entire range. And I'll show you that here in a minute when it is calibrated. There we go. So we just click done. I'm going to save that into slot 1. And you can see there that we've got a relatively nice flat line. It looks like it just sort of rolls off a little bit here in the top end above 170 megahertz, but we don't need to worry too much about that because we're not going to be measuring up there. So now that we're all calibrated up and we're saved, we need to go back to our display and then trace. I've just got trace 2, which is the green trace turned on. If we go to our channel, select S21 through. If we're on S11 reflected, that's not what we're measuring. We're measuring our through the VNA. And format S21 through, we want log mag. So you'll see here up in the top here, S21 log mag, 10 dB per scale. And at the moment we're zeroed out minus 0.03 dB. So 0 dB across the range. And that now we're good to go. So I'm just going to put this clamp now over the cable. I'm just going to do one turn, one pass through here. So we're just clamped in the middle of the cable, and you'll notice that that is our trace. On our 2 meter frequency here, we've got minus 2 dB. So 2 dB of suppression on 2 meters, which is not a lot. If we move our marker along and we find where it dips, the dip looks like it's down here at about, probably around about 20 megahertz. So about 5 dB down at 20 megahertz. So it's a little bit better down here at HF. It starts to roll up. What I like to do is I like to measure the 3 dB points. That's the half power. Then that will give us the bandwidth of that particular single turn of this ferrite core. So 2.92 dB, so around about 5 megahertz, we're going to say. 5 megahertz there if we keep on going until this number gets to 3 again. About 70 megahertz. So 5 to 70 megahertz is about our bandwidth of this device. Anyway, up here at 140, we're kind of not all that great. It's only about 2 dB. I mean, there's a little bit, it's better than nothing, but it's not a lot at all. And that's with a single turn through our piece of wire here. Now, if we go and we add a second clamp on, let's just go and see what happens when we do that. Our line has changed a little bit. Now we're at about 3 dB. So we've increased a little bit there on 2 meters. If we move this back down, again, our dip is about at 20 megahertz. It's about 8 dB. So we've increased because we've added that extra clamp on. If I go and put a third clamp on now, then naturally we should see an even larger dip, which we kind of do. Here at 2 meters, it's gone down. Now we're at 5. You notice that it's relatively flat as well, which is good. So if we go down here, you can see that there's a dip again at about 20 megahertz, minus 10. So that's about 5 dB better than just one clamp. And up here on 2 meters, we're about minus 5. So about 4 dB better than just one clamp. Here's where it gets interesting though, because if we go and remove 2 of these clamps, and what I'm going to do is I'm going to pass this wire through twice. So what we'll do is we'll just undo it from there and we'll pass the wire through again. And there we go. So we've now got 2 turns through this clamp. Let's just have a look and see what happens. Remember, we only had 1 turn through before and we had about 1 dB down, 1 dB of suppression. Look at that, 5 dB of suppression. So we're getting as much as having 3 clamps on here with just 1 extra turn through. You can see there that it has varied a little bit as it moves around, but we're getting just about as good. And if we move down here to about 20 megahertz, we're at 13 dB as well. So the suppression is much better with an extra turn through. So naturally, you would think if we have that, let's go and put an extra turn through, because surely putting an extra turn through should mean that it'll go down even further. So let's do that. So this is simulating if I put through my Ethernet cable through twice through here, through 2 turns, looping it through, then I should get more suppression. Well, let's have a look and see what it does. Well, definitely at the lower end, you can see here that that has dropped quite dramatically. At the lower end, we're down to 20 dB, which is really good. If we go here, it's off the scale back here at 3 megahertz, it's over 12 dB, and it's all the way up here to about 135 megahertz. But something interesting happens. Here at 2 meters, I've put that extra loop through, but we're back at 1 dB. It's not as good anymore with 2 turns through instead of just the 1 turn, instead of just the 2 turns, 3 turns instead of 2. So it's interesting to me that I would have thought that I'd just keep putting more and more turns through and I would be getting more suppression across the entire frequency range, but it doesn't seem to be the case. We've got 1, 2, 3, 4, 5 turns through there. So all of a sudden, we're starting to get a very sharp dip now at a particular frequency. So at about 17 megahertz, we've got this real sharp dip. We've got over 30 dB now of suppression on that wire through that core. You know, that's covering not too bad, 20 dB at 3 megahertz, all the way up to sort of 30 megahertz, 25 dB. That's going to work very well for HF, but not so much for 2 meters. 2 meters, we're actually above the scale now. It's plus 6 dB. So that's interesting. That sort of shows that no matter how many more, if you put heaps and heaps of turns through, sometimes it doesn't help depending on the frequency. So obviously, because I want it for 2 meters, what I would do is I'd take these turns off and I'd go back to my single 2 turn, or not my single, but my 2 turns through. So I've got my 2 turns now through the core. Now if I add another core here with another 2 turns, because we've established that that's what we're looking best at on 2 meters at least before it starts to, we start to lose a little bit, and we're looking like that. So now we're a lot better now. We're sitting at 11 dB or 10 dB down here at 2 meters. You'll notice that it's pretty flat across the frequency range that we're looking at. In my particular application, this has been good because I can look at this result and go that if I kept wrapping more and more turns through this core, it's actually not going to help me on 2 meters at least. Now, some of you in the comments might be a little bit smarter than me and you might be able to answer why that happens. I have read some information as to why it happens, so I kind of have a little bit of an idea, but I'm interested to see what you guys think, especially when I've gone there and wrapped more and more turns through, why I'm getting, you know, worse response up at that higher frequency. I think what I'm doing is I'm creating a tuned or a resonant circuit, I guess. And what these ferrites are doing is they're reacting on one frequency much better than all the rest. Now, if I go to let's go to a mix 31 here. Now, this is obviously not going to work for something that I can't disconnect, but what we'll do is we'll just pass this single wire through. If you can disconnect your wire or your cable or whatever you think is interfering, maybe it's a power cable or something, and you can pass it through this, then this will work for you. So we're just going to put a single pass now through this Mix 31 core and hook that up, and you can see there that we're pretty much not showing anything at all. There's a little bit down here towards HF just below the line, so our 0 dB line, but it's not really showing a lot at all. Let's wind a couple of turns through here and see what happens. Now remember that each pass through the ferrite is a single turn, so I've got 1 turn, 2 turns, 3 turns. Let's go 4 turns and just see what happens. We're looking not too bad here at 2 meters. We're at about 8 dB. It starts to drop off there above 2 meters. Reasonably flat all the way down here, the HF spectrum. So sort of 16 dB. So that anything, as far as I understand and what I've read, anything below 20 dB is really good. But if you can't get there, or you're only got like 10 or something like that, it's still better than nothing. So if you've got some ferrite cores and you're getting something around those sort of readings, then definitely don't give up. Just keep playing around until you get something that's sort of half reasonable. So 2 meters, 8 dB, that's not too bad. Let's keep going. We'll add some more windings. Now, as you're doing this, because you'll get a transformer effect, you don't want to go all the way around here in a single direction. You don't want to sort of exit out this side, the same side that you input, due to some interaction that you'll have. So the best thing to do is to cross over here in the middle of the core, and what we'll do is just keep winding through here so that our wire exits the other side. I think I've got the same amount of windings there on each side now. So we've got our input and our output on either sides of the core, and let's have a look and see what our response looks like now. So definitely down at HF, that is looking pretty good. 2 meters has sort of stayed about the same. It's quite a dramatic drop off here at about 120 megahertz, but everything sort of below 6 meters is better than 25 dB, 27 dB there. So that's actually a really good demonstration there that in this case, more turns is definitely better on the HF bands. Because I've got a couple of other cores here that are these beads. And what I'm going to do is, let's pass through here on each side. We'll go twice. So we'll go twice here at the start of the wire, and then we'll go twice here at the other end of the wire, and we'll see what this looks like. Now obviously with these beads, you have to install these before the cable goes on. So if you are installing any cables and you want to put some ferrite beads over the end, then this would be a good choice. Now the reason I've shown you this is because I've actually tested these already, and you could see, look at the dramatic effect that that's had. So we've got 16, 17 dB down at 2 meters, and we're looking very nice and very flat here across all the way up to 200 megahertz, all the way down to, there's 6 meters there, 16, all the way down into HF. So this would be very, very effective, but I've got the problem that I can't install these on already pre-made cables. If I had new cables, then I could definitely do it. So I've got a couple of clamps here that I'm not sure what type they are. I have no idea where they came from. I got these years ago. I just found them in the junk box. So I kind of want to see what these are like. So what I'm going to do is I'm going to test this big one first. And we already had shown that we get quite a substantial increase once we do 2 turns through. So let's just do 2 turns through the middle of the wire here, or roughly the middle of the wire. And that's showing pretty similar to what we had on the other larger clamps here that I tested earlier. Let's try this smaller one and see what this shows. I'm going to do again 2 turns through, and that's roughly around about the same. It's not looking as good as we've seen with some of these other options. Now here's a little core that I found, and I actually wrapped my USB lead around one of these. I think this is an FT140-43 toroid, and the USB lead came from my radio, went into my computer, and the problem that I was having was that my radio, when it transmitted, would drop the USB connection. As soon as I put this on, it fixed that problem. So I've done a video actually on doing that and fixing that problem. If you want to view that, that'll be up in the cards or at the end of the video. But if I wrap this through a couple of times here, and we can see that it's actually not too bad. It's looking here a couple of turns there through on 2 meters, 6 dB. It happened to be HF. So we've got a bit of suppression down there at HF, which when I did the turns through, I probably did 3 or 4 turns, and it works all across the entire HF band. So you can see there that I'm getting about, on this core, about 4, 5, 6, 7, yeah, lots and lots of suppression, enough suppression anyway. And here's a little interesting experiment that I did. Here's 3, so I've roughly got 1 here at the start, 1 here at the end, and 1 roughly in the middle. And if we actually have a look at the response here, this is probably the best response that I've seen. Here on 2 meters, we've got over 20 dB of suppression there, and as I move my marker along, we can see that, well, there's quite a substantial dip down here at about 100 megahertz, but moving up, we're better than 20 dB all along the entire, well, most of the HF band. It starts to roll off or roll up here towards the top end of HF. If I take that one off the middle, you can see there that we still get reasonable performance, and in actual fact, that's almost as good, if not better. That's better. That's 21, 22 dB. If you want to learn more about the VNA, I've done a couple of videos on this. They will be linked over here on the screen, and also how you can stop WSJTX from crashing using one of these toroids. The link for that video will be over here.